In this video, we will understand the Mulliken symbols for the two-dimensional and three-dimensional functions. In the last video, we saw how two or more functions are closed under a symmetry operation. For example, in the octahedral point group, dxy, dYz and dxz are mixed under C3 axis of rotation, and they can be transformed into each other under the symmetry operation. But they never transform to any functions other than dxy, dYz and dzx. Similarly, dx square minus y square and dz square are partially closed under the same C3 axis. These closed and mixed functions form a multidimensional irreducible representation. If there are two functions that are closed, then we will call it two-dimensional functions. For example, dx square minus y square and dz square in the octahedral point group. If three functions are closed, then it is three-dimensional. For example, dxy, dYz and dzx in the octahedral point group. To understand it clearly, we can take the example of square planar geometry, which comes under D4H point group. Here, dxz and dYz form a closed function under the C4 rotation about the principal z-axis. So they are the two-dimensional representation. The dxy is transformed independently, so it is a one-dimensional function and is represented by b to g. The dx square minus y square also transforms independently, so it also comes under one-dimensional representation, which is b1g. And dz square is also a one-dimensional function represented by a1g. The meaning of b1g and b2g have been discussed in the previous video. Two-dimensional representations are represented by E. Its character under identity element E is 2. Both Mulliken symbol E and identity element E are different. There is a reason behind the character to be 2, which we will discuss in the subsequent videos. E can be further divided into two groups, EU and EG. The symbol U and G are used to represent whether the functions are symmetric with respect to the inversion or not. If it is symmetric with respect to the inversion, then it is G, otherwise it is U. Similarly, three-dimensional representations are represented by T and its character under identity element is 3. They can be T1G, T2G, T1U, and T2U. The term G and U are decided by the inversion operation as in case of E. But the subscripts 1 and 2 do not have the same meaning in three-dimensional representations as they do in one-dimensional representations, such as A1G and A2G. In one-dimensional representations, the choice of 1 or 2 depends on whether a function is symmetry or antisymmetric with respect to a fixed secondary symmetry element of the point group. In contrast, for three-dimensional representations, 1 and 2 are used to distinguish between two inequivalent sets of three-dimensional functions. This distinction is determined by their overall transformation behavior under the symmetry operations of the point group, not by a single fixed secondary symmetry operation. For example, rotational axes, such as Rx, Ry, Rz and quadratic functions, dxy, dYz, dzx, transform differently under certain symmetry operations of the octahedral group. They belong to two different irreducible representations. Therefore, Rx, Ry, and Rz are grouped under T1G. And dxy, dYz, and dzx are grouped under T2G. In short, 1 and 2 represents how two sets of three-dimensional functions transforms under all the symmetry operations of the point group.